Hey everyone, welcome to another episode of Robo Papers. Super happy to have with us today Nishanth Kumar, one of the co-authors for this paper called From Pixels to Predicates, Learning Symbolic World Models via Pre-trained Vision Language Models. Thank you so much for coming to the spot, Nishanth. Maybe as a start, if you can share with us a little bit about yourself, that'd be great.
Yeah, absolutely. Thank you for having me. Very excited to be here on RoboPapers. So my name is Nishanth. I am currently a fifth-year PhD student at MIT, advised by Leslie Kelbling and Tomas Lozano Perez, and collaborating with a bunch of other folks in CSAIL. And broadly, I work on the intersection between classical robotics using search optimization and I guess these days people would call it maybe something like post-training or test time scaling, something like that. But yeah, broadly planning plus learning to try to solve long horizon complex tasks.
Very cool.
Very excited to get to share it. So, okay, so what I think a good overview, what exactly are we doing here? My advisor likes to ask oh, what's the IO spec of your method? So the IO spec of our method here is that we take some human demonstrations. There's another thing that I will talk more about in a little bit. It's really skills. We're assuming there's some sort of library of skills, but sort of human demonstrations and skills. And the demonstrations here look something like this. I'll sort of talk more about what's going on there. And the goal is we want to typically or popularly in learning from demonstrations, we seek to learn some kind of policy, right? Some kind of way to behave in the environment. Here, we're actually seeking to learn transition dynamics. So we want to use the demonstrations to learn some kind of model. And importantly, that model is going to be somewhat abstract. For people who know about robot planning, classical planning, task and motion planning, which I can explain more, it's going to have the structure of those kind of models that we typically write down for those kind of methods. But we're going to learn this kind of model, and the benefit of learning this kind of model is that we can apply it to solve similar tasks in completely new scenarios in a kind of zero-shot way by leveraging search. So we learn this model from the human, and then we sort of upload it into the robot's brain, and we put the robot in a completely new environment, and it should be able to solve similar tasks, given that we give it particular goals. So that's sort of the highest level thing that we're doing in the goal of this paper. Does that make sense as a introduction?
Yeah, absolutely. Could you maybe say a word about what predicates are then?
Yeah,
what do we mean by that? What do you want from these, and why is that important?
Yeah, great question. So I think I will talk about that and then actually also show some of the predicates that we learn in a simple environment. So predicate is a binary classifier. So what we want from a predicate as roboticists is we want to take in sensor data, ideally, and we want to be able to classify whether or not certain concepts are true. And each concept corresponds to a predicate. I think for example, a simple predicate that people talk about a lot is is the robot holding something or is its hand empty? So, that's binary. So hand empty is a completely binary predicate. It doesn't take in any arguments. But some predicates like holding, it might take in an argument, like an object of a certain type. So predicates are sort of these object-oriented classifiers is maybe one way to think about them for people familiar with object-oriented programming. And I think intuitively the way to think about them is as a set of concepts, right? So as humans and in language, we think about adjectives and stuff, and I guess nouns to some extent to describe the world around us. And predicates roughly correspond to things like this. So I don't know, is this to the right of this other thing? Am I holding this object? Is it soft? Is it wet? Is it this sort of thing? And if we can come up with the description of the world in terms of these predicates, then we can try to leverage them for very, very efficient search. And that's something that has been studied for a while. They're, I think, useful as a way to describe the world that leads to very efficient decision making. And so concretely, in this kind of domain we have here, we give it a bunch of demonstrations. This is a somewhat simple environment. I think this video here, maybe I'll show it full screen, is a good example. We want to I don't know, we want to wipe this table. So there's an obstacle. We want to like throw it away. And then we want to like pick up the eraser and use it to execute this wipe. And so for doing something like this, we might need some concepts like, is an object on the floor or not? Is an object an eraser? Are we currently holding something? Is there any object on top of the table surface? Is something on, or is our hand empty? These sorts of things. And if we use this, then I will talk about like learning transition models in terms of these predicates. But if we use this, then we can maybe efficiently solve some problems that have to do with this simple kind of table wiping scenario.
Gotcha. Nice.
Yeah, so I think actually related to that, another point about predicates is that we want them to be like generic. So we want them to transfer across multiple environments. So like this predicate, like, is an object an eraser, should ideally apply for like any object, right? Every object is either an eraser or not an eraser. Ideally, like, so I should be able to use this predicate with objects and maybe with in environments that I haven't really seen before. And hopefully if we can do something like that, we can like get transfer is of the concept, at least, is the idea.
Is that
Yeah, Nisha, I have a question. So how do you come up with the predicates in the first place? Because I suppose they are task oriented. I mean, specific to the task, specific to the environments. Yeah. Could you comment about that?
Yeah. So great question. So this gets quite a bit into our method. So maybe I will actually jump to the paper here and like use one of the figures.
Yeah, we can absolutely go into the method and stuff. This is like
Cool.
the
Perfect.
preliminary part. Like, what is the? Yeah, we can absolutely go into the
Okay.
content whenever you're ready. We don't need to.
Perfect. So here we go. Yeah, so good. So, okay, like as a sort of prelude to the method, what I want to say is that like, okay, so like we did not come up with the concept of a predicate. A predicate is something that has existed well before robotics even. Like it's been studied in computer science, in like formal logic and stuff. People think about predicates. And then the robotics community, specifically like the planning community, started using predicates as a way to write down like what was called planning models. I think we call them symbolic world models because really what they're doing is they're trying to describe some kind of dynamics of the world at an abstract level. And an important thing about predicates is that, so, you know, circa like 40 years ago or something, before modern AI, there like planning and predicates were like the thing that AI people thought was like how intelligence worked. And in particular, using predicates, we would make these like transition models and then do some like very, very efficient search. And people thought that, oh, by running some very long search on some very big model, we will get like intelligence roughly. I think one of there were many reasons. This was like called like for historical reasons, like symbolism, right? And the sort of symbolic planning paradigm. And one of the reasons that struggled was because it turns out that the world is very, very complicated, and trying to write down predicates, especially for like robotics tasks, is like really, really, really hard. And so from a planning point of view, I think one way to view this paper is like, we want to not have humans have to write down these predicates and figure them out. We would like to, you know, once we have the predicates, we have a whole bunch of methods to try to exploit them to do like problem solving. And we would like to invent these predicates automatically, right? So with ideally no human input. And, you know, the year is 2025. So how do we sort of do this? Well, we can ask a VLM, right? Is maybe one way we can think about that. Getting into concretely answering your question, Michael. So basically what we're interested, so I think one way to like look at these predicates, like if you kind of stare at them, things like, is this adjacent to this other thing? Like, you know, each of them, they're asking a yes/no question. And we know that VLMs are good at visual question answering, right? Like this is a thing that they were sort of trained to do. Like given an image and like a question about the image, can you like render an answer? And really these predicates are all just like binary questions about images with certain objects. And so if we want to invent predicates, we need to do two things. We need to first come up with like, well, what are the even predicates that we might be important? Like, you know, as you were saying, Michael, like, you know, in this environment where we want to like wipe, or where we want to like dump or something, the predicates are going to be very different than like an environment where we're cooking or we're doing something else. So we need to come up with like, what are even the concepts that we care about? And then the second thing that we need to do is like, given a predicate, we need to define its like classification function, which is like, okay, given a new image, how do I say yes or no? Is this predicate true or not? And the way that we do both of those things, I think one central insight in this paper, which is maybe not surprising, is that we can use a VLM for both of those things. We can't directly ask a VLM for both of those things, but we can leverage a VLM for both of those things. So what we're going to do actually is maybe, let me see if there is a good figure for this. Actually, I think in the appendix, there's one that I might point at. Oh no, okay, we might have taken that out actually.
That's okay.
So I will just use this. So basically what we're going to do is we're going to like, our method is roughly going to be kind of like 2 phases. So in the first phase, we're interested in even like trying to see what predicates might be important in this environment. So we're going to take the demonstrations, right, which are videos. We're going to label the videos with like, oh, hey, between this part of the video and this other part of the video, the human was executing this skill. And by the way, robot, you have this skill. So it's like, oh, between here and here, I was moving. Between here and here, I was like picking up this thing. Between here and here, and you also tell the system the particular objects that the human was interacting with. But these objects are just names that are passed to like a object detection system kind of thing. And then you just pipe this into a VLM and you just ask it, hey, can you propose a bunch of useful concepts? Like anything under the sun that you think is relevant in natural language. So maybe from our human demonstrations of like wiping a table or dumping like a trash can to get an object out of it, something like that, you might get proposals that look like, is this table adjacent to the trash can? Is the trash can containing, like can contain the apple? Stuff like this. These are just like arbitrary natural language strings that we just asked the VLM saying like what might be relevant here.
Is there a reason you ask for like arbitrary ones instead of like asking it to produce the predicates necessary for a planning problem? Or
Great question. So the reason actually turns out to be empirical. So I think the easiest, so we tried that. We have a baseline for that. And we basically found that this was like the first thing that we tried in this method and it does not work as well, is maybe a short empirical answer. But I think there's an interesting conceptual thing there, right? Which is that when you're trying to solve planning problems, there's something very important about connectivity. So, you need to make sure that you have a very small set of concepts that allow you to chain your skills together, because that's like fundamentally what you're trying to do. The other thing is that the VLM maybe doesn't know about its own uncertainty. So if you just ask the VLM like, hey, come up with a bunch of concepts, it'll come up with, or the concepts that are relevant for this problem, it'll come up with things that sound interesting, but don't actually transfer that well to other environments is what we found. So there's some element of what I would call maybe prompt optimization in the predicate names. So like, we actually found like, for example, is trash versus is trash can gets classified, like has different levels of accuracy.
Gotcha.
And so the procedure that we opt for is having the VLM generate a whole bunch of potentially relevant things, and then we run like a learning procedure to filter that.
Gotcha. That makes sense.
So that works better than just asking the VLM to directly generate the right things.
Right. Yeah, because some of these like is trash, as you put, and adjacent look maybe too specific. They look not general enough, right?
Exactly.
Yeah. Okay. That makes sense.
Exactly. Also, like, if you collect we can't pipe the entire demonstration set through like a VLM, like it exceeds context, even if you have like 10 or 12
Sure.
demonstrations. And so you end up piping them one by one. And then that like, of course that's going to go away when people have much better long context VLMs, but yeah.
And sorry, Nishanth.
Yeah.
So these predicates, it persists through, let's say, the entire, let's say, it's a 1 minute demonstration, let's say, so-called long horizon, it persists through. But then when you label it, is almost at a frame level,
That's correct. Yeah.
Okay.
So, right. So we ask for all the predicates. What we actually do is we chop the demonstration to before and after every skill execution. So actually, I'm going to jump back to a video now because I think we have a nice illustration of this in a video. So let me share my screen again real quick. Yeah, so okay, so this actually I think takes through nicely. Okay, so here's like one demonstration of me like putting this apple away, putting this like block away, and then like wiping this table. Okay, yay. Here's another demonstration of me like, here's a demonstration. This object is originally in this can, and then I need to like dump it to get it out. And then because I only have one hand in this demonstration, and then I need to like put it in this other thing. Okay, so what we're going to do is, okay, so we kind of chop up the demonstration to before and after every kind of skill execution. So we have some like library of skills and we're saying, oh, hey, here there were like 4 skills, like dumping and then picking from the floor and then placing inside, whatever. And then when we hand things to the VLM, what we're going to do, another thing I should mention is that we do tell the agent what the goal is. So we were saying, we say like, hey, the goal here was this predicate that we provide to you saying, hey, the goal was to get this green object inside this box. So we chop up the demonstration to be like before and after frames. And then in each particular frame, we label all the different predicates from the image that I showed you previously as to whether they are true or false. I can doing a little bit of jumping.
You meaning the
back and forth.
the GPT here, your
Yes,
LLM
the
does.
VLM labels. Yeah. So to jump back to that figure, so here, right. So we chop up these demonstrations and we have these like proposals from the proposal phase, and then we just label all of them with true and false in the like labeling phase. And sometimes the VLM says, I don't know, and then we just like default to false. So anything that isn't true, we just, because it's like safer to like default it to being false. By the way, because like true things we are going to like try to like take as evidence of like change or like learning. We're going to try to learn that when something turns false to true, like something has happened that we should check. And so if we turn false, then...
Why is that? Why that doesn't quite make sense to me. Like, what if your goal is to make something false? Like,
oh, cool.
Should...
So that's actually a quirk of the way that we use predicates. So we only allow... So if you want to negate something, you have to invent a predicate with a not in it.
Okay.
So you have to invent an inverse. We don't allow negation, but that's like a logic thing, and we could, you know.
So if your goal is to take
the
the apple off the floor, then I see the not on floor predicate there, and so that the goal would be to make that one.
Exactly.
Okay, gotcha.
Exactly. Right. And yeah, we should really do away with that, but that's like kind of an artifact. But yeah, for that reason, we sort of default to false. But yeah, so I think like to explain sort of the method, what is going on is we take these demonstrations, we send them through 2 phases. We send them through a proposal phase. We aggregate all the proposals and then we label them. So at this point, we have a labeled set of predicates. And what we want to do is we want to prune this set to a very, very small set of predicates that allow us to generalize, right? Because if a theory has very, very specific predicates, then probably it's, in standard machine learning fashion, it's like overfit to the demonstrations that it's seen. It's unlikely to generalize. But if there's like 0 predicates or very, very few predicates, it's probably too general. You know, we're going to admit too many solutions via our search, and not a lot of them are going to be correct. So we want a compact set of predicates. And then importantly, we want like a transition model over these predicates. That's going to be in the form of operators. I think I can show like a couple examples. I'm happy to get into the details of like how operators work and what operator learning does and like blah, blah, blah. So here's like a relatively simple kind of operator, right? An operator is really just if-then conditions, I think, is the easiest way to think about it. If the robot is holding some sort of object, then if it executes this place skill, the robot's hand will become empty, the object will become inside the container, and the robot will no longer be holding that object. That's what this operator says. And it's sort of lifted over objects, so it can operate over any object and any robot and any trash can. This gets invented. Yeah, so this is an operator is sort of a compact description of a transition model in terms of the predicates. So what we are interested in doing in our method is basically like, okay, we have a whole bunch of labeled here. So we have a bunch of labeled predicates at various time steps in a trajectory, and we want to learn a very small set of predicates and some operators that allow us to describe all the demonstrations as compactly as possible is basically the thing. And it would be great if I think like we could do this with some like cool, like if we could do this via gradient descent or some sort of optimization procedure like that. But this is all very non-differentiable, and like, we want a set of predicates and operators that lead to good planning. Planning is based on search. Search is non-differentiable. So this is like problematic for like applying gradient descent. So we actually apply like a non-gradient based optimization procedure. In particular, we apply hill climbing search, which is really just try adding one predicate, learn some operators. Does it lead to like efficient planning? Yes, we have like a function that measures how efficient planning is. And we basically keep adding in predicates and learning operators with some like classical algorithms for doing this until we find a theory that allows us to plan very efficiently in each of the demonstration tasks. And we also have a regularization term for how complicated the theory is. I think
I was going to ask about that. If you don't, so how would you differentiate between like a precondition or something that just is always the same? And I guess that's from your that's this regularization term that you mentioned.
Yeah,
Gotcha.
yeah.
Okay.
So I think actually a good intuition, like there's a lot of details in how this works, and that's why our appendix is like 20 pages here. And I would actually be super interested in, I think some good work like a lot of work to be done in improving like the learning mechanisms and making it like better here. But I think a good like conceptual way to think about this in an imitation learning like way is like, okay, so in standard imitation learning, right, you get some demonstrations and you try to learn a policy and you penalize the policy for deviating from the demonstrations, right? Now, here, instead, what you do is you say, well, I don't want to learn a policy. I want to learn a world model. So one of my terms is going to be the complexity of the model, because I want to learn a simple model. The second term, importantly, is going to be if I learn a particular model and run search in that model, does it produce traces that are close to the demonstrations? So the more close it is, the better that model is. So that's sort of the way to think about this in terms of like a loss function and like standard learning, I would say.
Yeah, so essentially the operators that you described are learned.
Yes,
And
they are
the way
learned as
you
well.
learn it, I see. But basically operators, it seems to me, yeah, it's you have all these label and proposed predicates, and then you try to learn what is the minimal, like, but still good way to represent the actual policies by limiting it to the minimum set of predicates that actually makes a difference. That is able to reproduce what you actually so-called observe in the original demonstration.
Yeah, that's exactly right. Yeah. So, and in particular, I think what you just pointed out there that is important or cool is like, yeah, we have all these labeled the operator learning part in particular, we have these labeled transitions, and many of the transitions use the same skill. Like in a couple demonstrations, we've seen wiping, right? And what we're trying to do is kind of cluster those transitions together and then take what are the predicates that were true before? That's the precondition. What are the predicates that, like in common, become true, like go from false to true? Those are the add effects. What are the predicates that go from true to false? Those are the delete effects. So it's roughly some form of clustering these transitions, but there's noise. And so you have to do some like noise tolerant kind of clustering in the operator learning procedure. But operator learning itself has been studied as a subproblem for a very long time. And so we're lucky in that we can lean on some kind of algorithms there, but they're all basically clustering based. And then so the procedure is the optimization procedure sort of at the highest level kind of goes as follows. And I think we have maybe an algorithm here. Yeah. Okay. Here we go. So there's math and symbols here, but like the idea is that J is our like objective function. And what we're going to do is we're going to just say the objective is decreasing and it's greater than like some minimum threshold. What we're going to do is we are going to look at all our candidate predicates, and we're going to identify a subset, and we're going to try to learn operators on that subset using this clustering technique. This gives us a particular world model. And then we're going to run search in that world model, and we're going to compare the trajectories to the demonstrations. And then we're going to take a loss. And if it goes down, then that subset is a good subset, and we should keep it and then try to grow it at the next iteration. But if it doesn't go down, then abandon this and move on.
Kind of reminds me of like inverse reinforcement learning in some ways too.
Yes.
It's constantly, yeah.
Yeah, I think it's like so we take a lot of inspiration for this kind of thing. There's a whole area of like program synthesis that people work on, which is like, given a couple examples, how do you learn a compact program that describes those examples, like in Excel or something? Given some examples of like a calculation, can you learn a formula or a function that describes a calculation? And that also has this flavor. But yeah, hopefully that sort of, at least at a high level, makes some sense.
Yeah, so.
Cool. I think that is actually like a pretty good overview of the method. And so I can maybe go into some of the results if there's no other questions.
Yeah, let's do that. That sounds great.
So, okay, so I'll talk about some maybe quantitative results first, and then I think the real fun thing is seeing the robot videos, and I'll talk about the robot videos and everything that we needed to do. But just to quickly talk about some of the quantitative results and so this is like, we wanted to show that this is kind of like a general method for like sequential decision making in like environments where you can describe things with predicates and you want to do some like long horizon tasks. So, we did two major real robot environments, but we took 3 environments entirely from like previous papers and tried to run them. And you can see like 2 of them are like actual like 3D robots, and one of them is like this weird like Overcooked or Grid World version of Overcooked kind of simple game.
It's been a while since I've seen that one, but
yeah. And this is like, making burgers or something like this. And what we do is, I think like this is like a good summary. So the x-axis is like success rate. So what we do is, for all the methods, they all get the same number of demonstrations that are generated, and they can do some learning. And then we just eval them on some held out set of tasks in new environments, right? And the held out tasks tend to have more objects, like more complicated goals requiring more steps, like obstructions, that sort of thing. So we're testing like, can you like actually generalize based on learning some kind of concepts? Like in burger, we're saying, hey, I showed you how to make a cheeseburger, and literally only a patty. Well, okay. Actually, separate demonstrations, I showed you how to put cheese on a burger. I showed you how to cook a patty, and I showed you how to chop some lettuce. And now I want you to assemble 5 full burgers from these like very separate demonstrations. So this requires some set of combining the concepts and then stitching together the behavior needed to produce them. And so that's like a critical aspect that often imitation learning struggles at, that we wanted to tackle with our method. So, the top line is ours in terms of the success rate on the held out tasks. So this VLM subselect baseline is actually, we'll ask the VLM to propose the full set of predicates, but then we ask it to subselect what it thinks are the most relevant predicates for the problem. The no subselect baseline is, we actually just tell the VLM, hey, there's no subselection phase. You just tell us which predicates are the most important, and we'll try to do operator learning from there. This is not important. This no feat baseline is like something that's relevant to the environments. I don't think it's that useful. No invention is like, you don't get to learn any predicates. You don't get to do, really any like learning. You just try to take the task and like run a planner using the information you have. And that does not do anything in any of the environments, unsurprisingly, because we haven't learned any sort of predicates. Okay, and so there have been some approaches in the literature recently that have used a VLM to write programs that can be can sort of act as predicates. So they write like functions and stuff. But so this is like a previous method that does something like that. And we find that, well, allowing the flexibility of predicates to be natural language and not just like functions that call like object detection modules or segmentation modules or something like that is very important. Like concepts like, you know, is the cheese melted? I wouldn't even know how to do with object detection and segmentation. Right? You just want to ask a VLM. I think
So
the
what's
most
happening here there is that one is applying to, I'm assuming that kitchen boil kettle is one that is mostly seen, or what
Yeah,
is the difference between?
exactly.
Okay.
So in kitchen boil kettle, the reason this kind of works is because your demonstration time, you see turning on a knob and then pushing a kettle to the burner that you turned on. And then at test time, you're asked to like turn on more burners and push the kettle to one of them. And it's purely like object based. Like you're just trying, you put this VLM learns to put a bounding box around the kettle and a bounding box around the object. And then the planner is just like, oh, I just need to
Okay.
move
And
them
because
together.
those two things are in the test case exactly. for this, there's no-
Exactly.
okay. Whereas the other ones are the generalization. Okay, gotcha.
Exactly. There's no difference in
Okay.
objects in kitchen between the train and test. Like it's the same because the
Yeah.
environment was designed that way. But here there's like less lettuce and more lettuce. And here there's like less coffee and more coffee and like
Oh, I
different
see.
machines and stuff like that. So that's where the VLM feature predicate fails. So Vila is maybe the most interesting thing. So that is the closest thing to a pure imitation learning baseline. So there, we just take all the demonstrations, we do the same pre-processing that we do for our method, but we just put it in context to a VLM, and we say, hey, generate a plan.
All right. I was going to ask where this baseline was. All right.
Yeah.
Okay. So it is actually there. Yeah, that makes sense.
Exactly.
Why is it called Vila? What's that?
So Vila is this, so basically there was this paper called like Look Before You Leap, like unveiling the power of GPT-4o in like planning. And this was basically the first ever look.
Okay.
We just did planning by asking like a VLM for robots. And so we adapted that to the few shot. Okay, you do the planning conditioned on some demonstrations that have some skill information in them, kind of a thing. So
did you do a version without the in context part?
Yes, so Vila is no in context at all. It's just pure planning, and then Vila few shot is we do the in context.
Okay, so the VLMs on their own aren't able to handle predicting these complex plans. Okay, gotcha.
Yeah, and I'll say I'll say from having worked on this that I think VLMs have like come quite far, but there are a lot of corner cases when you're doing like real robot like planning. Like it gives you a reasonable plan. But like, I'll actually show. I think now is like a good.
It's often reasonable, but not executable. I think.
Yeah, okay. Exactly. Semantically reasonable, but not as executable. And we actually find in cases where the demonstrations are super varied, and you're really trying to stitch different aspects of the demonstrations together at test time. The Vila is like, I don't know what's going on, and just tries like somewhat random stuff. So we actually demonstrate this in an environment. So this was like, I think maybe the highlight of, at least for me, of this paper, these two different environments. So, okay, I will maybe full screen because it's easier to see. So what we did was we took 6 demonstrations that looked like this, right? Of like me and my like robo-hand like going around and doing this sort of thing. And we ran our method and we got a set of predicates and operators. And what we did is, okay, so the first thing we did is in the same room with slightly different objects, we run the method. And I played this video earlier. You get something like this, right? So the robot never saw this blue coffee cup at training time or this like table. But because the predicates are things like is eraser and is blocking, and they apply over any object, we can just like zero shot and do this. So that's cool. But I think the real power is like, and this was kind of fun, we straight up just like took the robot to a different room at MIT. So this is like a classroom that is in the like neuroscience department that fortunately no one was using. And we used the same predicates and operators that we learned from those demonstrations in that other room. We gave it this goal where we said, I want you to throw away it's like a cleanup inspired scenario. So throw away this soda can. And then I want you to wipe this table. And then importantly, I want you to take this sponge thing and put it back in this trash can, like, or in this holder thing. And importantly, the sponge is inside the trash can or this holder to start out with. And in the demonstrations, the robot has never seen a scenario where that's true. It has separately seen scenarios where the sponge is on the floor and it needs to pick it up and use it to wipe stuff. And separately, it's seen scenarios where it needs to get something out of a container by dumping it and then picking that thing up and using it. So here it has to like kind of combine those like ideas together. So yeah, like it needs to like dump and wipe. So, okay, so here's Vila. So Vila Few Shot in particular. So we load all the human demonstrations as context, and then we just ask a VLM to do things. So, okay, the first thing that it does is it tries to pick up the trash can, or sorry, it tries to pick up the thing inside the eraser, but it can't because of its hand, and so it ends up picking up the trash can. And then it tries to pick up the table in this particular case. I don't really know why the VLM decided to plan like this from its demonstrations, and then it tries to like throw away the thing. And basically the point is the plan is like kind of weird. And I think it's not surprising given that the demonstrations are like pretty different, and this is like a very different environment than the demonstrations were given in. So I don't know, it just seemed confused. Okay, but our method using the predicates and operators that we learn is like, so it decides to throw away the soda first because it knows that its hand is going to be full. Like it knows that it can't pick up the sponge and use it for wiping if the soda can is on there. Its hand is going to be full if it's holding the soda can. So it throws away the soda can first for that reason. It dumps this thing and then it picks up this eraser and like it wipes this table. There's like some marker stuff that you can see that's getting wiped away, and it checks that the wiping is done, and then it is done. Okay, and it completes the task. Now, something I should mention that's also kind of cool about this method is that, we can just replan at every step. So, every time we execute an operator, we know what is expected to be true. If that is not found to be true, we can like replan accordingly, right? So the system can be made reactive through just replanning. So here is a sort of demonstration of that. Let me skip ahead here. So the robot has wiped it and then like showed up in this gremlin costume to add extra sort of stuff on the table. And it checks and sees that, oh, okay, the table has stuff on it. My goal is not complete. What do? I need to wipe it. I need the sponge. Oh, wait, I'm holding the sponge. Okay, let me just execute the wipe action again. Look, the table's complete now. Okay, I can be done. So that was cool, seeing it generalize like that. And then I think so that environment was somewhat simple to sort of cap off our results here and just show off like the main, like, I don't know, maybe headline result. In that wiping environment, maybe some of the predicates are simple. I think given a VLM, maybe as a human, I could write down those predicates and like get it to work, right? But the whole point of this method was we want to invent and learn predicates and operators for like complicated domains that like humans don't really want to write down, or it's like really complicated, something like that. So we bought a juicer off of Amazon that like is a little bit complicated to operate. And so, okay, the juicer like separately separates out waste and juice from this thing. And like, here's like a sequence from a demonstration. Okay, you pick this thing, you like put it in the juicer, you like close the juicer, or you close the lid of the juicer, and then you turn on using this thing. And then, yay, we have some juice in this particular plastic cup. So we took 10 demonstrations that sort of look like that, and we end up learning a pretty complicated theory that, you can see. It's a little bit... The predicates here are super interesting. It's like things like, are you inside the valve, or is the cup near the valve enough to be used? And like we're able to plan in this like new scenario that we haven't seen before, where one of the cups is present, but another is not. And we need to sort of set up the cup and then make some juice. And the juice actually fills into the thing, which is cool. But just like the previous demo, we can zero shot this in like a new environment by just loading in the predicates and the operators, and we can make some like pear juice, which I didn't know was like a thing, but you can in fact juice a pear. And it doesn't turn on the juicer before getting the cup because it knows that that's going to spill, or like it didn't see that in the demonstrations. It learns properly that there needs to be a cup, and so it's able to put it there. And okay, this skill kind of doesn't make the thing as close as possible to the thing. You will see that actually there's like, it's hard to see because pear juice is like empty, but there's like a bunch of spillage that happens, unfortunately, and we don't get it perfectly. So, but we can make some pear juice, and I think that's kind of cool.
Yeah, Nishanth, I have a question. How, like, that who picked the? Presumably, you train your you learn a bunch of different operators. Like at test time, like how do you tell the robot which operator to use? Does it choose from a plethora and then decide for itself, or?
Yeah, it decides for itself. So we just give it the goal, which is, so here's actually like all the operators that we learn in this like kind of juicing environment. I think there's like 13 or something of them, and they end up being somewhat complicated. Some of them are like, there's one for closing the lid, there's one for picking, there's one for placing it inside the juice valve region, etc. And we just give it the goal, hey, there's this cup, this like purple cup or something. We want to put juice inside of it. You figure out how to chain the operators and with what objects to pass into their arguments in order to accomplish the goal. And that's like search.
Got it. But it looks like there are like something like 12 operators here, right?
Yeah.
Something like that. But I presumably you have hundreds of operators. So how do you pick the 12 to use here?
Oh, so that's part of the learning procedure. So at learning time, given the demonstrations, we are learning predicates, and those predicates lead to like, we have a pool of like hundreds of predicates, and that pool leads to like maybe millions of operators. And our learning procedure is like trying to find a subset of the predicates and operators that explain the demonstrations. And this 12 is like the thing that came out of our optimization, admittedly with a bunch of hyperparameter tuning that was necessary, but yes, you get this compact set of 12 operators from the learning.
So this is the 12 operators just for juicing, right? So
yeah.
I guess, so continuing with Michael's question though, so could you, like, I guess if you wanted to like deploy this in a home and have people give it arbitrary questions, could you just pile all your operators and learn predicates and demonstrations together, presuming context length wasn't an issue?
Totally.
Is that closer to kind of what you're getting at, Michael?
Yeah. I see. Yeah. So so these operators were learned just with the juicing demos. Now, there's no reason why we shouldn't, in principle, be able to put all the demonstrations we've ever seen and put it into this thing and then learn some like big set of operators. And then, now we have theoretically operators for everything. We have thousands, millions of them, something like that. And then given any goal, we need to so there is an area of research that figures out, given a goal, if you have millions of operators, how do you find a subset that is useful for that goal and then run search in that subset? Theoretically, you could just run search amongst the millions. It's probably going to take forever, but you can do that. But yes, in principle, we could put all the demonstrations together and learn like a very big theory. Now, practically, there's some limitations, we have not solved all of planning or world models or anything in this work. And one of the limitations is, I was mentioning how our learning algorithm is like non-differentiable and like, it's basically amounts to some kind of hill climbing over like our big set of predicates and operators. That's slow. The more demonstrations you have, the more varied predicate proposals you have, which leads to like a very long search time. Or very long learning time in order to like learn this sort of thing. So I think definitely there needs to be like, along, if this vein gets continued, which I hope it is, there needs to be more efficient optimization algorithms for like learning this sort of thing. Maybe one could make it differentiable. I think that would be really cool. But in principle, we have talked about one thing that could be cool. You could take a bunch of YouTube demonstrations or something of like humans doing tasks, and theoretically, if you had a powerful enough optimization procedure, you should be able to learn a very large collection of predicates and corresponding operators that describe all those like demonstrations. And then maybe you'd have a symbolic like or abstract world model of like this very large corpus of like video data that from humans' use, which would be interesting.
Do you think it helps you to debug? Because it just strikes me that this concept of predicates, it's very logical to human. Like I feel that every time you throw into a big machine learning thing, you have no idea what's going inside. You can only observe the output and control the inputs. Here, you can kind of like, does it help, or is it like just too many operators also?
Yeah. So this is actually a great question, and something that didn't really make it into the paper, but like something that was very interesting as like someone developing this method. So for the juicing and for the cleanup as well, right? Um, our algorithm has a bunch of hyperparameters, right? Just like any machine learning system, right? There's things equivalent to, like, even in the loss function, how much do you do regularization? When do you like stop the thing? Even what are the demonstrations that we show, and how many demonstrations do you need, right? All this stuff. And so the way that we were able to get this juicing and this cleanup working is by actually, we started with the demonstration set. We ran the algorithm, we saw what it learned, and the predicates are all natural language, so we can interpret it, right? And we see it doesn't realize that its hand needs to be empty when it's picking. Okay, we should add a demonstration that shows that thing. Or like, oh, the theory is way too complicated. Like, it thinks that it can only wipe surfaces with green erasers. We need to like reduce the like complexity rate, things like that. Or the regularization term. So something that I think, as a machine learning practitioner is like kind of cool is that this is like, it's not the most interpretable, because ultimately, like, you're coming up with a bunch of hypotheses, you're shoving them through this optimization algorithm, you're getting something out. But each of those things is like debuggable somewhat, right? You can say like, oh, hey, that's a wrong concept. It didn't get it right. And okay, now I have some sense of what to tune. So this actually ended up being like, I don't know, usually I find myself when trying to get robot demos working, just trying different hyperparameters and hoping and running sweeps, right? But here I was like, it was like a human in the loop gradient descent kind of thing. I was like, okay, it doesn't understand this. Okay, let me add this demonstration. Oh, now it understands this. Okay, let me reduce and then you sort of converge. So it would be cool. I think that's one of the benefits of this style of doing things.
Yeah, I think, that's the thing that strikes me. Like, it's the predicates are all very humanly understandable concepts. And yeah, I think the reason why I asked the earlier question, it just strikes me that, like, in theory, if you have a huge egocentric video library, you can learn presumably a huge predicates, a lot of diversity, and also a lot of operators that once it's trained up can be reused and repackaged and then do really, really long horizon task. And
That's
still
the
make it,
dream.
it's quite, I mean, debuggable. Because I think the issue with all the end-to-end learning stuff is the longer horizon you get, it is very hard for you to know where things break, and you don't know what kind of new demo to collect to fix it, so-called. Other than just blindly dumping, okay, I just need another million hours and hope that this will,
Yeah. Yeah.
whereas this one, you can be very, like, with human in the loop, because humans are still way better than the embodied AI thing. So you know the specific thing. I'm curious though, like, as this VLM become, even way more powerful, do your earlier example of the VLA baseline at the villa, will catch up, or you think there's just something fundamental that, what do you think?
Yeah, that's a great question. And I don't know, I think it's like an open question. So, okay, I'd put it a little bit like this. So, okay, I think that if you look at a lot of the tasks that people in the planning world think about, right? Classical planning has these like competitions. And if you look at the benchmark competition tasks, they're these like super intricate logistics tasks. They're like, I have like 20 planes here and there's all these people and I need to like send them places. And graph search just makes a lot of sense for logistics, right? VLMs and LLMs, I think, are really, really good at like kind of common sense planning, right? Like, hey, how do I make a chicken sandwich? And I think the question is, for the tasks that we're interested in as roboticists, how much of it is like this complicated logistics thing that needs something like graph search or optimization versus just kind of common sensey things? My sense is it's mostly close to the common sense thing. So because of that, you can always find an example to trip up a VLM, but I don't know if the point is to try to trip them up, right? Like, the point is, can they do the job for the set of tasks that we're interested in? Now, I do think, though, maybe a takeaway of this paper, or like, even if VLM planning gets better, like, and like we're able to do a bunch of tasks. I do think like one of the things that like a search or like an optimization or something in a world model is going to get you is like, hey, I can explore multiple solutions. I'm not getting stuck with one thing, like some sort of robustness, right? I can find multiple paths, that sort of thing. And VLMs, based on the way they're trained, the fact that they can plan is cool, but it's like emergent. But the fact that they can recognize concepts, the fact that they can like look at images and answer questions, that's what we train for, you know? So maybe like we can use them to be good recognizers, and we can use like other algorithms or whatever to like be good reasoners. And then we get like a more complete system. I don't know. Maybe the VLM, like, you know, you bake this stuff into pre-training and then it's like a reasoning VLM and it just figures this stuff out. I think that would be interesting as well. But I hope that maybe long-term this work, maybe not the specifics of it, but it inspires more kind of like interpretability, like we were talking about, and like concept learning and like using different systems in a modular way for the right things or for specific things.
This is actually one of the things that I thought was interesting about this. Along a similar line is that like if you look at how these like we're in the year of the agent, right? That's Sam Altman says, right? And the way that agents work is that they always break it down into sub pet tasks and reason over what the requirements are and build a plan. And like it does seem like this is just, I don't think we have an analog for robotics yet. And so it's very interesting. And predicates are kind of like a neat decomposition where you have to figure out, because like it is a visual task, not just a textual one like modern agents work with. It's like, how would you do this? Anyway, so it's at least gets you thinking. I think it's a cool.
Yeah. Yeah, I agree. You know, I've started working on like computer agent planning and stuff somewhat recently, just in my own PhD and stuff. And there's analogs, and I agree. I think like what is the right decomposition in robotics, and how do we for things like computers, like, oh, there's code and there's HTML on websites, and the substrate and like how you make plans is like somewhat clear, but in robotics it's not as clear. We adopted predicates just because of the history and because, you know, there's tools to deal with them. I don't know that predicates are like the right answer here. I think that remains to be figured out, but you know, I think hopefully it inspires some future work in these avenues.
Yeah, I think the other thing that attracts me to this approach is I mean, typically when you do like physical tasks, there's a lot of like qualitative aspect to the whole thing, whereas you put it into predicate, you're forcing it to be true or false, and it makes it like it suddenly become very quantifiable. And then once things are, you know, not stochastic, it's more deterministic, then you can do all the other things that people have built, like algorithms, you know, that has been built already around these things, and you just leverage those very, you know, like efficient search algorithm through very deterministic things. You don't have to rebuild like probably decades of work already spent on it. We don't just throw away just because now we have end-to-end. Yeah, especially when the end-to-end barely works in robotics.
I think it's gonna, as someone who's been working at the intersection of like this planning and learning stuff, like, yeah, I it feels like there's a lot of work that has been done that's cool. And, you know, people have worked on like, hey, what if your predicates have probabilistic values? That's a whole area. And there's techniques for like, oh, I'm going to reduce my uncertainty and partial observability and all that. I think that's really cool. I think it would be great to put everything together. But maybe, you know, like that stuff needs to be moved into a neural paradigm. It's unclear, right? Like in this work, we sort of take the neural thing to invent some symbols to then put it into a search paradigm. But maybe the search process needs to get moved into something that's a little bit more neural. Like there's a whole bunch of ways that people are trying to figure out this integration. But I think it's exciting. It does feel like a lot of work has been done, and it feels sad to throw it away.
Yeah, I mean, the operators are the one thing that always seems a little odd to me. Like the fact that they are very symbolic and very fixed. Like if they were neural, that would make a lot more sense almost, because, you know, like most interactions are not particularly deterministic based on some fixed set of conditions, especially if you have an image of the scene you care about. Yeah, anyway.
Totally.
But like, the other thing is that because I used to work on predicate stuff back in my PhD, and like a lot of people have, and like one thing that I think is also nice is that like defining them is just a real pain in the ass. Like it really sucks, and like the in context demonstration gives a really nice way of grounding like what it actually means to be close enough to the spigot or whatever it was. Like that's because it's just such a pain to actually decide,
right? Come up with thresholds, exactly.
Yeah. Right.
Anyone who's worked on planning has had to like hack on like
right.
what's the implementation of my predicate classifier? And yeah,
Right. It's a much cleaner way of doing it, I think. Yeah, that's good. Cool.
Yeah, well, I guess yeah, Nishan, you talk about a bit of the limitations and just now. So I guess yeah, future work like are you thinking about like just doing even way more like demonstration across even longer horizon tasks? Is that what you're thinking about, or?
So I think that yeah, so I think one exciting thing that I hope to pursue, we'll see bandwidth of that, graduation, etc. is so last year at Coral, Tendra Malik gave a keynote that I learned a lot from and enjoyed a
Yeah,
lot. One of the
library
things
of
he talked
70 skills, I think. Is that the one
sorry,
you're
yeah,
talking?
yeah, exactly,
Yeah,
exactly.
that rings a
So
bell.
he
Yeah, yeah.
yeah, so
Public
to give a
skills.
quick
Mhm.
recap for maybe people who haven't heard of it, he talks about how he took a video. Him and his colleagues took like a video data set of like from movies and YouTube and whatever, and basically they like manually annotated skills in like roughly every frame or something, and they were like, look, 95% of human action of the things humans do in like these 10,000 hours of video or something boils down to 70 skill invocations, something like that. Okay. I think it would be pretty interesting if we could take a data set like that, type it through something like this, and get out like a crazy large symbolic description of the world. And then given any initial frame of that video, can we come up with the activity set for the entire and a final frame, right? Like, oh, a goal or something. Can we come up with the set? Okay, here's the set of things you need to do in order to like achieve this. So if we did something like that, that would just be cool and interesting. And maybe it would give some idea to hold on like this hypothesis or this idea that, hey, most of the things we want robots to do is describable in this like fairly compact model at the abstract level. And now, of course, implementing that, learning the skills, etc., that's like problematic. And a whole bunch of research needs to be done there. But this important hypothesis that, hey, we have now all the concepts that are needed to describe like 10,000 hours of like human activity or something, and we can like make plans that do super long horizon tasks in this like sort of thing, would I think be like a pretty cool result that might be like interesting and might impact how robotics goes forward. I think that would be cool. And then yeah, can we do more complicated? I think another thing that I'm personally interested in working on is like, so all those skills that you saw, like turning the knob and like all this sort of thing, those were all like semi hard coded, semi like, learned by like me and co-authors, right? Now we're starting to have these powerful VLA models. Can we like integrate those and then do some like joint hierarchical, like, world model planning plus low level VLA skills in some nice way? I think that would be cool too.
Yeah, I think
Cool.
okay, I have
Good.
some idea for you already.
Okay, I would love to hear it.
But yeah, but maybe just I guess I don't know, Chris, you have any more questions? But usually we like to ask this like just to wrap things up, like any other like cool papers that you come across recently that you want to give a shout out to. It doesn't have to be exactly about predicates and whatnot, but you think yeah, you just want to highlight.
Yeah. Good question. So, okay, there's actually, I'm forgetting the name of this paper, but it was from this new professor named Pan Kai in, I believe, Singapore. She wrote this paper, she and her group wrote this paper about doing this, like, hey, we took like a bunch of tasks and we learned like 1,000 predicates and like hundreds of operators or something like this. And it was cool. I sort of skimmed it, but the like effort and the fact that they like sort of really scaled this kind of search and predicate style thing was really cool. I will definitely give a shout out to that. I have been looking a little bit into this like into this VLA Pi 0.5 like weights just came out. I've been playing around with that, and I have to say that's like a really good paper, like very mainstream, very good paper, and like very good work. So that's cool, and you can download it, and it just kind of works. I think at least right now, those are maybe the two things that I've like looked at and like have been reading recently that have been really cool.
Cool. Thanks.
Yeah, awesome. Well, yeah, thank you so much, Nishanth. Thank you for all the sharing. Yeah, personally, I think that this is quite refreshing. We've done nearly, I don't know, 40, 50 episodes. As you can imagine, it's mostly end-to-end learning, take out the humans in the loop.
Yeah.
I think that to me, a lot about that. I think for me, the interpretability of what your work does, I think is very appealing to me. And not just appealing because I can interpret it, but also I think it has a lot of pragmatic like outcome. Because if the end-to-end thing doesn't really work, like it's still only at 99% when you need 99.99999%. Like you don't know what to do next, like other than just collect more data, right? Whereas this one, you can actively debug it, right? Okay, this is, so I thought that one is actually really cool. Yeah. And I think, Chris, to your point, when you were, I think, working on predicates, like now we have this VLM tool that basically take all the burden away. So you can actually scale that part, the predicate and then the operator learning.
Yeah. That's always been the problem with this stuff is does it scale, right? And the answer historically has been no. I'm hoping that it changes. I'm hoping you change that.
Yeah, we'll see. Yeah, no, thank you so much for the invite and for the kind words. Yeah, I don't know. I'm glad. I think something my, I don't know, like my advisors, they have a lot of experience. They've been around the block a lot, and one of the things that they've been saying recently to all their students is like, hey, like, a lot of cool stuff happening in the end-to-end paradigm, but like, we don't, maybe as a community, we don't want to put all our eggs in one basket of like, is this going to solve robotics or not? And, as much as sometimes it's like hard to listen to them or etc., they do kind of know what they're talking about and they have a point. So I really respect, it's good to be advised by them, and they've really pushed me in like new directions, and I'm glad you found it a little bit of a breath of fresh air.
Yeah, I think so. Okay, thanks so much, Nishanth.
Thank you.
Looking forward to your next paper. Okay. All right, Chris, what have you learned today?
So I thought it's a really interesting kind of different direction than we usually see lately, which is more on the symbolic planning side. Like, how do we use VLMs to set up like a symbolic planning problem and break down a bunch of human demonstrations into pre and post conditions that you can then sequence to generalize to new environments. I thought it was really interesting stuff, very thought provoking, some nice discussion. Like we were talking about at the end, I think the biggest problem with this area has always been whether or not it scales. And like, I don't think we're quite there yet, but this really, like, you're starting to see like the pieces, seeing how it might actually get there, which I think is really exciting, because then you can do like really crazy stuff with robots, have them think and reason over longer horizons. So anyway, what did you think? How do you like it?
Yeah, I think the VLM is a big unlock, right? It's all this manual work that you used to have to do during your PhD, let's say. It's a VLM can automate like very effectively, and I think, I don't know, it just makes very logical sense to me as a human that like if you want to do very, very long horizon tasks, you probably need something like that so that you are not always in this. I think that the longer really long horizon tasks, let's say you ask someone to cook up Michelin star level kind of like a 4-course dinner, right? That is like I don't know, thousands of subtasks in between, right? Or maybe even tens of thousands. So for those stuff, I don't know how do you do this end to end, like,
But I mean,
like, so something like this make it a lot more tractable, because if it doesn't work, you just figure out and then look at the like the operator, is it like the operator, look at the predicates, analyze as a human, because we understand these things very, intuitively. You don't need a PhD to analyze it. You can just ask a high schooler to look through it. Probably can tell you, okay, it's and then okay, then you go out and collect the demonstration that is specific to that, and then you do it.
Yeah.
So
I mean, this is one of those things where I think these have always been like cooking your 4-course Michelin star meal or whatever it is. Like, if you could write the planning domain for that, like any of these classic methods could solve it, like without like really quickly. But the problem's always been grounding all the different symbols, which he just showed us how you can solve, right? And then it's like building the domain, which he sort of showed us how you can solve, but I think there's still some stuff to do there as far as building a really big correct one, right?
Yeah, I think that
and also learning the skills, which is tricky, and we've talked to lots of people about how to do that.
Learning skills probably still have to do like the I don't know, meditation learning, like that kind of thing. But this one really helped to solve the long horizon planning and make it really tractable. And I think this paper doesn't solve I think the question that I asked, that which you kind of reinforced, which is I mean, what you really want is just a plethora of predicates that, and an operator that's already been, learned that you can just take, but the question is you will have like maybe thousands or maybe even millions of these operators in theory. Like knowing at inference time which one to use is also quite critical.
Yeah.
So it's a search step, right? I mean, yeah.
I think
So
that's
this is the right step. Right step the step in the right direction. I think for a very, very long horizon thing. Yeah.
Yeah, I mean, this is how people solve long horizon tasks, right? So you figure out, okay, so to cook this meal, I need to, I don't know, maybe I need to prepare chicken. To get the chicken prepared, what do I need to do to do that? I need to get out the dishes or something. I don't know, right? So there's we break it down into like this, and I think it's always such a cool thing to think like how we can do that for robots. That is anyway.
Yeah. If I tell my wife that, then you probably even before that she would say, okay, like you go and buy the chicken first.
Sure. Yeah.
And I would need to make myself navigate to the shop, to the grocery store, navigate to the store. Like it's all these are just subtasks. To actually cook a meal, you need to get the ingredient, and that is also physical.
Right.
We can't just assume the ingredient to show up in the fridge, right? Anyway, very cool. I'm glad you brought this paper. Yeah, brought Nishanth to come out. Okay, I guess
Awesome.
until the next one.
Yep. See you next time.